So in the yesterday class, basically we took the task of image classification and started discussing a simple classifier like a k-nearest neighbor classifier and how it will perform on a reasonable data set like CIFAR 10 class label data set. And also we discuss a better classifier like a linear classifier, which basically where there are some parameters for the model which are learned basically. So the input, so this kind of a classifier has some weights, and basically the prediction is basically a function applied over the weighted sum of the inputs. And this function can be is normally in a good function is a sigmoid function, which is also called logistic function. And in that case, this is called a logistic regression classifier. So this sigmoid function will basically predict probability value between 0 and 1, depending on whether the class is. So it is for binary classification. And so we also discussed basically how do we learn the weight. So for learning the weight, we need an optimization function, and a good choice of an optimization function for this will be a maximum likelihood estimation, which is basically proportional to the posterior probability given input x, and for a particular set of model parameters, calculate the output probability for belonging to class y. And basically, so for each sample we calculate that probability and multiply it to get the cumulative probability. So, and assuming each sample is independent and all that, so the total probability, the maximum likelihood will basically will be the product of all probability. And to basically now, using some simple mathematics, we obtained this kind of an expression basically, which needs to be maximized in this case because we want to maximize the likelihood. So we can learn weights by maximizing this, so that those set of weights which maximizes this function will be a good weight for this classifier. So in practice, we take the log likelihood because it basically simplifies the solution. Instead of product, now you will have summation, and you also avoid some numerical underflow cases. So when the probability values are too small and you multiply all of them, the net result will be a very small value. So you avoid all that by taking log likelihood. And you can take derivative and then try to do an analytical solution, but for this function, if you do this, take the derivative, you won't get a closed form solution because this sigmoid function is an exponential function, nonlinear function inside summation. So unfortunately, there is no analytical solution known for this thing. So normally, but good thing is that this function is a convex function. So we can go for an iterative optimization method, like a gradient descent method. So gradient descent basically so if your optimization function is a convex function basically, and you want to find the local minima or maxima basically. So depending on the gradient, so the gradient for this function, so for this type of a convex function, on this side of the curve the gradient has positive value, and this side of the curve the gradient has negative slope. So here there is positive slope, here there is negative slope. So if you want to move towards the minima, from any point you should move in the opposite direction of the gradient. So if you are in this direction, you should move. To move towards the minima, you have to go in the you have to do a decrement. So the gradient is positive, and you have to take a negative of that to move towards the minima. And if you are this side, you have to basically move in the opposite direction because the gradient is negative here, and you have to add the weights. You have to increment the weight in this case. So iteratively we keep on doing this and slowly we converge towards the local minima by taking this kind of a gradient descent approach. So the equation for modifying our weights will be like this: the current weight at particular iteration t, we basically take the gradient of the function with respect to the model parameters and go, because we have to move in the negative direction, so we take a negative of that, and multiplied by the step size. So how fast we want to go, basically that depends on the step size value. So you can increase the step size, and accordingly you keep on updating the weights, reach towards the extrema. So if it is a likelihood function, it will be this kind of a function. There you will be trying to ascend up the curve. If it is a loss function, it will be this kind of function, and you will try to move towards the minima. So now for gradient descent, we need to calculate this gradient value. And to calculate this gradient value, you will have to basically calculate this for each sample in the data set. And if the number of data samples are very large, then this can be a little bit computationally prohibitive. So normally we do an approximation, we do an estimation. Basically, you go for a stochastic gradient descent. So in stochastic gradient descent, basically, instead of taking the entire data set for calculating the gradient, we take some random sample. So random sample is unbiased. So by choosing a subset of the data set, so instead of for all I in the data, we calculate this gradient value for certain subset of that data. So we do a summation over some subset, and the size of that subset is called batch size. So this is one of the hyperparameter that you need to set, how much batch size you decide for training a model. So in the extreme, you take the entire data set, but then that will make your training slow. Speed up your training set. Basically you take a subset and you reduce your batch size. So that is your stochastic gradient thing. And this we have already talked, loss versus likelihood. So your optimization function can be a loss function or it can be a likelihood. If it is a likelihood, you have to maximize it. If it is a loss function, you have to minimize it. And you can always change the sign to make a loss function a likelihood or a likelihood as a loss function. You can just change the sign also. So doesn't makes any difference basically. So in our case, in our logistic regression case, if we take this stochastic gradient descent, what will be the equation? Let us try to just understand and see how it works. So let us take the simplest case where the batch size is just 1. So you estimate the gradient by just randomly choosing just one sample in the data set. So in this case, our log likelihood function can be written as this. And if you take a derivative of this function, you basically it will come out this expression, and you can rearrange it. It will finally boil down to this simple equation or simple expression. And you can see this expression makes sense because let us just substitute this in our weight updation rule. So weight updation rule was basically minus neta times your delta gradient. Here, because we are ascending, this is a likelihood function, we are ascending, so we are taking the plus here. So now you can see how we are going to change the weight. So that depends on this value. Now what is this value? So remember, this is your prediction score probability from the sigmoid function, and this is your output label. So how far your predictions or your predicted score or predicted probability is from the actual output label, that gives you an idea whether the model is trained or not. So if the model is not trained, basically this difference will be high. So in that case, you will aggressively try to modify the weight. So when this difference is large, you will change the weight more drastically. Whereas when this distance becomes smaller, that means your predicted probability becomes closer to your actual ground truth label. In that case, this difference will become small. In that case, the modification that happens in the weight will be smaller. So so it will work out in practice properly, because that is what we wanted. We would like to update our weight in order to basically match our predicted probability with the actual output score. So this was for a simple binary classifier, but most of the time we'll have a multi-class problem where we have multiple classes like in UCFR class data set, you have 10 classes. So we can use a simple extension of the binary class logistic regression to multiple classes. So what we can do is basically we can for each class we can have a one logistic regression classifier. So for each class we'll have each set of one set of weight parameters, and then we can predict the probability for each class separately. So for ith class, we can do the sigma w1 wi xi. For I is equal to 2 class, basically we can calculate its own. It's another its own set of weights and input parameters and so on. Now, so each will give some probability value. Now, this is good only if your output classes are not mutually exclusive classes. So the more than one class label is possible. In that case, it is okay, because here there is no normalization being done. So all the probability values, if you sum them, they may be less than 1 or greater than 1. There is no normalization. So more than one output class may have high probability, or more than one class may have low probability, and so on. But in practice, we will mostly we have a case of mutually exclusive class labels. So one data sample will normally belong to only one class. So in that case, it's better to have a normalization. And to do a normalization, instead of normal sigmoid function, then you go for a softmax function. Sometimes it is also called cross entropy activation function. Or so this is kind of it's just basically a normalized logistic regression over across classes. So this is your net input to the model. Z is basically your wixi, basically summation wixi. So this softmax classification function basically says that it takes the basically score for each class, and in the numerator you see it is basically summing over all input classes. So this is a normalization factor which actually takes care of that. And how it basically, so it will generalize to the normal logistic class if there are only two classes. So that means Z0 is 0 and Z1 is Wx. If you simplify it, it simply becomes 1 upon 1 plus e to power minus Z, basically. So, but if there are multiple classes, it will do the job of normalization very easily. So an example calculation is shown here. Let us say you have 1, 2, 3, 4, 5 classes, and let us say your input net input to the model was coming out to be 1, 2, 7, 3, and 2 for different classes. So how this logistic function, this normalized softmax function will do the calculation. So e to power x of e to power 1 is 2.72, e to power 2 is basically this, and then this numerator is basically sum of all these e to power x's. So that gives you this one. So if you divide this each class score with this normalized score, you basically get these values for this particular instance. And you can see the one which has the maximum score basically is getting a probability score which is close to 1, and all others are getting score near to 0, and sum of all this score will be equal to 1. So this is basically a normalized probability score. So how do you choose which is the output prediction? So you just take the maximum one. So which one is the maximum? You basically choose that as the output label of that for that particular instance. So this is how you basically do for a multi-class scenario. You use a softmax function instead of a normal sigmoid function or a logistic function, and that helps us to basically develop a linear classifier for a multi-class scenario. So this is the same. This is just a logistic. So how it works basically, if you try to interpret this softmax classifier, so it is basically calculating the probability of a data point belonging to a class is basically just a normalized weighted sum of the input variables with the learned weights. So if you want to basically visualize this, so now instead of just one class, we have multiple class labels, and for each input, let us say you have 3 input variables, and for for each particular class, we will have one set of weights, and for other class we'll have another set of weights, and so on. And each one of them basically, when multiplied, and then you apply the softmax function in the previous slide. If you apply the softmax function, you get the output score, and this output score is normalized output score. So that, and then you basically predict the class label. This can also be written in simple matrix operation like this. So if you rearrange this weight, these model parameters for each class, so for each class weight will become basically a row in this matrix. So for the first class, these are the three set of weights. For the second class, these, and third class, these. So you can basically matricize it and then multiply it with the input x1, x2, x3, and this is the bias term. And this total score, apply a softmax function that will give you the output prediction. So how this will work, how this this simple logistic multinomial regression classifier will work. So if you take a simple classification problem like a handwritten digit recognition problem, there is an MNIST data set which is released by this American Institute, National Institute of Standards and Technology, something. They had released this, they had developed this handwritten digit recognition data set, which consists of, I think, 50 or 60,000 images. Each image is basically of size 28 cross 28 cross 1. So it's a simple grayscale image. And there are 10 classes. So number from number 0 to 9. So you can straight away, so for each image, basically you just flatten it out, all the pixel values. If you just flatten it out and make it a single vector of input, and you treat it as x1, x2, and xn, then it becomes a 784 dimension input vector. And if you apply this 10 class softmax regression equation like this, you will get and train it using this gradient descent and all those things, and using maximum likelihood function, then you will easily get an accuracy of 95% class for this problem, which is okay, reasonably okay, because probably this data set is very simple data set. But if you apply this this classifier on CIFAR 10 data set, where each image is a 32 cross 32 cross 3, because it's an RGB image, and so that becomes around, if you flatten it out, it becomes 3072 input values in the input vector. And if you divide over 60,000 sample images for training, you take 50,000, and for test you take 10,000, and apply this 10 class softmax regression and train with stochastic gradient descent, then you only get an accuracy around 40%. So in comparison to MNIST data set, where you are getting close to 95%, for this data set you are getting a very low accuracy with this simple classifier. Why? Can anybody guess why this data set will perform, why this this linear classifier performs poorly on this data set in comparison to MNIST? Because we are dealing with images, and this, you have identified, this is one of the major bottleneck here, as we are just using a simple raw input pixel values. We are not extracting some features, and raw input pixel values, as we have seen, you can see for a same class label, you can see raw pixel input values for different images within the same class can be totally different, because the background itself can be totally different, and the positioning of the object can be top left corner or right left corner, or the horse can be left facing or right facing, and so on. So those to learn all those variations using just raw input pixel value when given this, and also we are using a very simple classifier also. So that one problem is we are just using the raw input pixel value. We are not doing some high level feature extraction. The other problem is about the classifier also. Our classifier is too simplistic. So if you try to interpret the classifier itself, what this linear classifier is just doing, basically try to understand, it's a very simplistic. So in this case, for example, here, if you try to just visualize this on a, let us say it is just take the two-dimensional representation of our let us say image space was just 2 pixels. So we have just taken 2 dimension here. So our different images are basically like samples in this image space, and we are learning basically a classifier for each class, and it can those classifiers are linear classifiers. They are basically doing a linear separation, and now this problem here is we are making our dimensional space a very huge dimensional space because we are just using raw input 3072 pixels. So this becomes a very huge dimensional data space, and to get a good hyperplane which actually does this separation between the samples of each class will be very difficult on such a high dimensional space. Getting a good linear, good boundary between classes will be very difficult. For two problems. One is because we are going on a very high dimensional space, and another space we are just using a linear separation boundary. But the data set itself, the data sample itself may not be linearly separable. The data samples may not be so clearly linearly separable, and just using a combination of linear classifier may not be very easy. May not help us distinguish the data samples, and many nodes will be there, so training time will increase exponentially. The nodes are not here. Here the nodes are not. This is not a neural network, so we don't have multiple nodes here. We have just so training time is not a problem here in this case. Also, not every pixel is related to the other, so localization of the features is needed. Yeah. So there is so the spatial layout and the invariances of the things that have to be taken care, and those things are not taken care. So we'll come to that. So that is one problem with linear classifier. Another way to interpret this linear classifier, if we see those weights that are being learned, so depending on the number of input things, we are learning certain weights, and if we rearrange those weights into a 2D matrix, we can visualize it as an image, and that image is basically can be seen is it is kind of a template that is this classifier is basically learning a template for that particular class. So if you rearrange those weights into a 2D matrix and try to visualize it, so you can basically visualize it as an image itself. So you can see basically for each class, this is just a visualization of those weights that are being learned, and you can see probably it has tried to learn an overall shape of a car basically for this particular class. Similarly, for planes, basically it has learned this type of a template. So probably because majority of there was sky and all that. Similarly for ship, majority of the background was probably water region. So we have blue pixels here, and in between we have some structure here. So similarly horse, you can see probably there are both right facing and left facing horses in the data set. So what it is basically trying to do, so when you are multiplying this W with your X and trying to get a score, output score, so it is nothing but kind of a template matching thing. If you remember our template matching thing, if we take a template and if the template matches with our input image, then the score will be high. And if the template is not, it does not matches with that, the score will be low. So so it is trying to learn just a single template for the entire class, and if this template, when multiplied with a class with a data sample from a car class, probably that score will be the highest than as comparison to when the other templates when they are multiplied with that. But the problem with this is you are basically learning it will not generalize well because you are trying to learn a overall template which is basically, but this template is not capturing all possible variations or things in that data set, and it can be totally, sometimes it can be very lot different than the actual image. So so basically this linear classifier is effectively doing kind of a nearest neighbor classification only, but instead of now having thousands of training images with which you compare, now you are just comparing it with just one template image and finding out the distance from this template. So this is so both are problem. First of all, we have not, it's kind of like average of all the training images. Yes, you can say it's basically trying to learn some kind of pattern in that particular class. So there are two problems. First of all, we are not using a good feature space. We are just using raw pixels. So that is causing one problem. Another problem, our classifier itself is not a very robust classifier. It's just doing a very pretty basic task only. So we need to improve on both things in order to get a better job. So in mid 2000s, between 2000 to 2010, support vector machine was one of the popular choices for classifier because it is much more powerful than a simple linear classifier. So instead of learning multiple linear classifiers, it tries to learn a single max margin classifier. I'm not going to go delve into details of this because this is now no more popularly used. But it had been used for a long, and a lot of papers are written using this support vector machines. So just overview. So many times in many of the works, people have used support vector machine basically instead of simple linear classifiers, because this gets trained well on a small data set, and it does find out quite a good boundary of if the data points are linearly separable. If they are not linearly separable, there is a kernel trick possible. You can use some radial basis functions or other kinds of non-linear kernels. So some mathematical, it has some mathematical power to it, by which you can actually learn do a good job of classification, at least much better than simple linear classification. So it was used for a long time, and one of the particular a good example of success, which is considered at that time, was this object person detection, which was basically developed by Dalal and Trix in 2005. So they basically use histogram of oriented gradient features. So it's kind of a shift features, but much simpler than that, histogram of oriented gradient. And they use those features, and they trained using SVM. And they have this two classes, person and not person. And again, it was basically a sliding window detector kind of thing. So for different scales, for different locations, they will extract HOG features and then give it to the classifier and see the response. So something similar to the Euler-Jones phase detector, but now using SVM and different, instead of Haar cascade features, they use HOG features. And also there was some deformable part idea to it, because the object persons, unlike face, when we are detecting the entire person, the hands, legs, and all those parts are quite deformable possibility. So they had to take into account all those things. So they used so apart from just the base model, they used models for the different parts of the body and trained on all of them, and they use some kind of a latent SVM. What it is, I also don't know. So I'm not going to delve into details anyhow. If anybody is interested, they can read it, but I'm, in the interest of time, I'm just going to skip it. But this did perform very well, and for many years, it remained state-of-the-art detector for detecting people, persons in the images. So, but the problem in these kinds of approaches was people would be basically experimenting with different set of features, which features are working nice for this particular application, and then what kind of classifier is working. And it would be a lot of kind of a feature engineering, hit and trial, and basically all kinds of things. Basically a lot of experimentations to figure out what works well for a particular problem. And we have seen that different machine learning models, they work well if there is a clear relationship between input and output. So if inputs are, for example, if inputs are linearly separable, then linear classifier works well. And but if the inputs are not linearly separable, let us say this kind of input is there where the boundary is not a linear boundary, then you'll have to go for some other kind of things probably. So so you can so there are two things: either use a classifier which has non-linear boundary, or you transform this feature space itself. So let us say this was just raw input pixel, but if you extract some features or if you modify these features, so instead of using simple xy, if you take x square plus y square as a feature, as your new input, as your basically new input value, then this space distribution space get transformed like this. So this non-linear separation now can be linearly separated if you just transform this raw pixel values into a new into a feature which is nothing but just x square plus y square. So that means, and this kind of a feature engineering remained basically for many years. People were trying to do this kind of feature engineering, trying to find out how to transform our input raw pixel values, which features to extract, which features well in combination of. So different features will work well for different combinations of classifiers. And linear mod, we cannot, people could not learn those features automatically by just using a linear classifier, because if you just do a linear for linear classifier, is what it is doing basically, it's just applying a function over a weighted input, summation of weighted input, basically w1 x1 plus w2 x2. So this cannot so simple summation of wx basically cannot transform your features. At least they cannot transform your non-linearly separable features into a linearly separable features. So that was the bottleneck basically in the traditional machine learning methods that were used for vision. So again, summarizing it. So one part was trying to do static feature engineering, basically trying to experiment with different set of features, either using HOG features, SIF features, SURF. LBP is basically local binary pattern. We did not discuss it. Fisher vectors. These were some good features which were used. Or so people will basically use different combinations of this and try to extract some different set of features, and then apply different classifiers or family of classifiers like SVM or with appropriate kernels and or a softmax classifier and so on, and see which one will work better. So these things would go on, and whichever would give a better accuracy, it will be basically picked up as the model. So, but with all these things, people were not finding a lot of great success. So, for example, for this image classification, this ImageNet dataset is the standard dataset that was developed. Basically, it is a huge dataset which has 1,000 different classes. We'll talk about this later on, this dataset. But this, and every year challenge would be posed on this ImageNet dataset, and people will submit this different classifiers that they will train with different set of features, and the accuracy was bordering around 50 to 60% only with all these things. So for many years this remained things till this deep learning and all those this breakthrough happened. So what was the basic difference between the different set of approach that people started taking recently, or at least in the last decade? So the idea was, instead of ourselves doing handcrafted selecting features through static, basically manually selecting features, that is what we call handcrafted features. We would like to learn those features automatically. So our algorithm or whatever classifier that we are using, basically, apart from, in addition to learning the weights of the classifier, can we learn these features or automatically extract these features also? So to learn these features, basically, we will boil down to learning the weights or the kernels, basically, which when applied to our input image will extract certain features. So can we do this basically, or instead of just learning just one features, can we, so in the past people have seen that combination of features would perform well, not just only one features will not always perform well, having a combination will perform well. So that means we'll also, can our algorithm learn multiple such features or filters or kernels in addition to the weights of the classifier? So given an input image, can we learn multiple this kernels or filters, what we'll call? These are the terms basically now being used basically, but this is nothing but just a 2D set of your weights. So when those are applied to the input, they will extract certain features. When they are convolved with the input, they will extract certain features. Just like if you use a Sobel filter, it will extract edges, and so on. So so we need a method which can actually extract these multiple, which can learn these multiple filters, so that we can extract multiple features from the image automatically, and then train them on a classifier. So, and then also, as later on people identified that just one layer of feature extraction may not be so powerful. Having multiple layers of feature extraction is much more powerful, because it builds over that, because of our hierarchical nature of our vision and all those things. The need was to learn multiple layers of such filters, so that we can extract features in a hierarchical fashion, and along with our classifier weights. So that was the need, and people realized that it could be done easily if we just simply treat these kernels of filter coefficients as additional parameters of your classifier, and it basically will see this, and you can learn those along with the weights of these classifiers. You can learn these things also using simple iterative optimization methods and backpropagation algorithm, which is particularly for neural network. How can it be done? Basically, this can be done if we add little bit more processing or more power to our classifier. So for example, if let us say your raw input pixel values are x1 and x2, and if you can create new features using the raw pixel values or the old ones, using an additional layer of processing, which is also called hidden layer in neural networks basically. So you have, let us say, x1 and x2 are your raw pixel. If you take some combination of that, w1 x1 plus w2, apply some function which is not a linear function but a non-linear function, then you may be able to transform these raw pixel values into new features. Basically, you can create these new features, and just like with linear models, this hidden layer thing can be expressed also in simple matrix operations, x1 x2, and this you can rearrange these weights into a kernel or a filter as a 2D matrix w. So multiply xw and apply an activation function, you get the nodes or the outputs at the hidden layer, and these values can be considered as new features which have been learned from the raw pixel values. And then using those hidden value nodes or new features that we have learned, we can do a linear classifier and do a prediction. So assuming there is only one prediction, so we have just one node, but if you have multiple classes, then we'll have multiple nodes. So this kind of a simple neural network that we see here, this part of the initial part of this can be treated as a feature extractor, which takes the raw input pixels and tries to learn new basically features or extract features from those, and then those new features are then used, and then they are basically, the second part can be seen as a simple linear classifier, taking those new features that have been learned or reduced set of features or whatever, and then applying simple linear classification over it, using either softmax function for multiple class or something like that. And everything can be expressed in a simple matrix notation. So this layer was this, and the next layer would be taken by another this function. And hopefully you can see basically it's nothing but just something, we are just extending the same thing that we were doing. And in practice, this is just having one hidden layer, but you can have many more hidden layers in between, so that you can learn more features basically in a hierarchical fashion. And each layer is just some function phi applied to the linear combination of the previous layer. So basically you can in theory you can learn more and more powerful features using the primitive either the raw pixel values or more primitive features from the previous layer. You can learn more powerful or more high level features in the next layer if you go on adding more processing or more layers in between. And this is nothing but a simple neural network, feed forward neural network, which can do this thing. And the only thing is this function that you apply phi should not be a simple linear function. It should be a non-linear function, which is also called activation function in neural networks. And why this so? Because if it is a simple linear function, then again the transformation will not, if you can basically, this entire thing can be just written into a single matrix operation. So if phi is just a linear activation, then you cannot transform, you cannot manipulate the raw pixels more into a non-linear, you cannot transform them in non-linearly. You can just get a simple weighted average only, weighted product, sum of the weighted product only at the end. So that means your activation function has to be some more powerful functions, and it has been proved by some researchers that if phi is not linear, then you can actually, this kind of a neural network can model any continuous function which is bounded. So these are some technicalities, jargons. But in practice, it is possible to model using a neural network any kind of a function, a continuous function, using appropriate activation function on this. And how do you learn it? So I hope the learning, you already know how do we learn this weights in the neural network. Again, you use gradient descent and backpropagation things. So I'm not going to discuss this because you have already learned in your previous class. So we use basically, for each node, we basically calculate the local gradients and backpropagate the local gradients, and this way we keep on updating the weights and the parameters from the last layer towards the previous layers, and we keep on basically in that way we learn all the weights in the neural network. And I hope you would have also be familiar with different type of activation functions which are used in neural network. So logistic or sigmoid function we have already seen. Tan H is was also another function which was used for some time. Recently, people have started using ReLU and leaky ReLU. ReLU is basically a rectified linear unit, so which basically is 0 for negative and basically linear for positive things. And this tends to perform well for some regions, for training purpose and for learning, during learning basically, because what happens in this sigmoid function, basically the gradient at these points, when the prediction scores are at near the threshold value, the gradient function, the gradient basically becomes very low, too close to 0. So it's basically the learning gets hampered by that. But whereas this is not true in ReLU, because ReLU is always linear, basically in positive and 0 here. So this problem does not happen in ReLU. So for training purpose, ReLU works better at intermediary layers. And at the last layer, mostly people use softmax logistic layer because we have multiple classes. And the softmax function actually does good normalization of probability score. So we use those things at the last. Layer. We know, but the problem of overfitting and underfitting, the bias and variance problem, and the neural network can become very powerful. It can overfit the data if it is not taken care. So there is a regularization which we do. So while training, we need to take care that the variance does not becomes too high. Basically, it does not go for overfitting. And there are different techniques for basically training neural networks to avoid overfitting. One method is called regularization, which basically puts limits on the model. So the weight, so you basically add some weight terms, basically momentum terms and weight decay terms, so that weight do not go on increasing beyond limit, basically. Or other technique which is also used is called for dropout technique, basically. So in every iteration of backpropagation, you randomly delete some of the neurons. In that way, you avoid basically learning all. So because we are randomly dropping some neurons, basically it adds more robustness and invariance and generalization. It generalizes well. But if we if we have a lot of hidden layers and all those things and train it for all of them, sometimes the data, most of the times data tends to overfit on the for that particular network architecture. So by doing a dropout technique, basically you tend to take care of those things. Next class, what we are going to see is that if there are challenges. So neural networks in theory can work well, but in practice they don't work well for images because of many things, and that's why instead of neural networks, what works well is called convolutional neural networks for images, and that is will be the topic of our next class basically. So why neural networks don't work well in images, that we are going to discuss in the next class, and maybe I'll just give some idea about it. So on a simple data set like MNIST, neural networks can work well, and they give quite close to 98 to 99%, less than 2% error basically. So about 90 to 99% accuracy you can get. But for other things, it becomes little difficult, and there are many reasons basically. Some of the reasons are shown here basically. First of all, if you just flatten out your images to so for example in this MNIST image we have 28 cross 28 image. If you flatten it out, it becomes a 74 dimensional vector. It ignores the spatial structure of the input images. If you just unroll it, then you are not giving any importance to the spatial structure of the objects in the images. So there is you are basically treating each pixel or each independently as if without their spatial coherence, without the norm. So we have seen that in images local neighborhood plays a lot of importance in things. So there has to be some way to preserve the spatial layout. And also, so in this case, no obvious way for networks to learn same features at different places in the input images. So when we use these desk connections, we are not ensuring any kind of invariance. So for example, if you are learning an edge detector, that edge detector should work similarly for each locations. Or if an object is present, an object can be present either in the lower half or in the lower bottom or the upper left or the lower right and so on. So there has to be some kind of, we have seen when we are discussing features, we would like to detect features which are invariant to simple translation, rotation, or scale change and so on. So all those things are not explicitly treated in neural network, in a simple feed-forward neural network. And most important reason why neural network do not scale well for images is because the number of connections, the number of weights becomes too high. Just if, for example, if you consider a simple 1 megapixel color image, and if you take 20 neurons in the first layer, just in first layer you have around 60 million connections. So you get 60 million weights, and to learn all those weights becomes very difficult. So we are going to discuss this thing into more detail in the next class. What are basically drawbacks of traditional neural network based classifier, why they did not work, and then why convolutional neural network actually did the trick and started getting a very good result for these type of tasks like image classification and so on. So that will be our topic in tomorrow's class.